Good morning everyone, I am Mr. Ish. You are joining me here for this video on improper integrals, where we're looking at this whole type 1 style of improper integrals which have infinite intervals. I've presented a very generalized and simplified concept video on improper integrals. In this video we're taking that concept one step above for the type 1 style of integrals which have infinite intervals. My goal in this video is to make this difficult topic very simplified for all of you. I want to start this video here with a bunch of rules, but they're not difficult, and I want you to look at them with an open mind. And remember, in the previous video I was talking a lot about convergence and divergence. In divergence the limit would not exist, in convergence the limit would exist. What did all of that mean? We'll look at that in this video, and when I present these rules initially it'll make sense as to what I was talking about. Let's start with first this. If we have a situation of this, infinity a, the interval is that, and we have something f of x dx, I want you to view it in this following form, which will employ a limit. The form I want you to utilize is this: limit as t approaches infinity. We're now looking at this situation over here, and you're seeing there's nothing out of the world over here. I've employed a limit into this definite integral with an infinite interval employed. Look at this situation where we have a upper limit, could be a good finite number, but here we're coming from minus infinity. We have f of x dx here. Look at this entire situation as this limit as t approaches minus infinity. We're looking at this situation over here, and you can see it's nothing out of the ordinary. We're rewriting these integrands with infinite intervals with limit forms. Lastly, look at this more interesting form right here: infinity minus infinity, f of x dx. These are all type 1 improper integrals. Remember that. Type 1. Why? Because they have infinite intervals involved. When you see something like this in terms of interval, having a domain minus infinity up to infinity, bring an arbitrary value a and squeeze it in somewhere in between. So you're looking at something like this: minus infinity to a f of x dx, and then adding, because these intervals add, from a to infinity f of x dx, and then this specific part right here, you will view it now as you have noted here on the top: limit as t approaches minus infinity from a and t f of x dx. And this specific part will be noted as this: limit as t approaches infinity. You have the remainder of the expression coming into play. Look at all of this. Try to commit this to understanding and memory, because I'm going to present you a single good example in this video, all of which will bring this into good clarity for you with regards to what it meant that you had convergence because a limit existed. So keep this in mind. When you have an infinite interval, you can bring in a limit into play, and you can employ the limit to help you solve that answer and come with a good value. The single question, the good question, will evaluate, utilizing the information I've provided you so far, is this type 1 integral we have presented right here. An improper integral we have to evaluate from minus infinity to infinity, dx over 1 plus x squared. You know that's a very easy in terms of an antiderivative that can come about from there, but we'll talk about that. First we have to set this in terms of how we will evaluate this with regards to the rules I was presenting you. How about we look at everything as this: if a were to equal to 0, this is the intermediate value I'm placing in between a domain of minus infinity to infinity. We're squeezing this a value right here into this interval, and we're going to look at everything like this: from minus infinity up to this 0, which is a, and we have dx over 1 plus x squared, plus, then we're looking from 0 up to infinity, we have dx over 1 plus x squared. But what I want to do first, before I do anything further, is just evaluate this integrand. If we didn't have this infinite intervals involved, we're looking at something which looks like 1 plus x squared, and this, how do we go about doing it? I know I'm looking here at something which is an arctan, which you know is the same thing as inverse tan that, because if I did the derivative of this, I end up with that. The derivative of arctan x is 1 over 1 plus x squared. We know that from our derivatives in our integral videos, but hypothetically, if you didn't know any of this, how would you go about doing it? You'd have to think about trigonometric substitution. Here a is equal to 1, x is equal to tan theta, dx is equal to secant squared theta. Then you'd have to go through this longer procedure. Then you would plug in these items that you see, these trigonometric substitution items. You'd have 1 plus tan squared theta. Remember all of this. This right here looks of the form a squared plus x squared, which leads you through this set of substitutions. This is all part of trigonometric substitution integration techniques. Tan squared theta plus 1 is secant squared theta, which cancels out with this. We end up seeing just this, which is theta plus c. And you know theta over here was everything with regards to this. Theta over here is equal to arc tan x. And you know then your answer here is arc tan x over 1 plus c. All of this right here is similar to that. But we've already established, utilizing our library of antiderivatives, that this is coming from that. You don't have to go to this longer trigonometric substitution technique. Let's come back to this topic here. We have to think of this in terms of limit. Limit as t approaches minus infinity. Now I'm doing this exactly as the rule stated. Dx over 1 plus x squared plus limit as t approaches positive infinity, right? We have 0 and t, right? I'm substituting these infinite interval values with the letter t. Dx over 1 plus x squared. Now what we can do is actually evaluate this. When you evaluate this, we already know we have this limit as t approaches minus infinity. We have inverse tan x. You know, going from an upper limit 0 to a lower limit t, we can write that. And then we have this one right here, limit as t approaches positive infinity. We again have inverse tan x, right? Again going from upper limit now here of t and 0. You can easily do this utilizing the calculator or the graph. I will do this using both approaches. Why not? I know that the graph of an inverse tan has a y equals pi over 2 horizontal asymptote and y equals minus pi over 2 other horizontal asymptote, and it goes like this. It grazes, as you see, those asymptotes, those horizontal asymptotes. In terms of the limit placement, I'm looking here at the 0 coming into place of the upper limit coming into place of your variable, and then the lower limit and the difference of 2. I'm really looking at inverse tan of 0 minus inverse tan of t, which here is a minus infinity. We'll evaluate this, and let's come over here. Here I'm looking at inverse tan upper limit t coming into play. Remember, always upper limit, lower limit, and the difference of the 2. Here t is an infinity minus inverse tan 0. Let's use the calculator approach first, then we'll finish with that graph approach. All you have to do is hit 0 right here and inverse tan it, and you get 0. So we know from here we're getting a 0 right over here. Then I have this minus. For this part right here, minus infinity, you don't have to be too creative. You can just come up with a very large negative number. I'm putting all the 9s and I'm putting a minus. Then I'll do inverse tan and I get a minus 89.99, which means if you were to put larger numbers, you get close to minus 90. And here I'll put minus 90, which is a minus pi over 2. Let's bring this plus over here. Now let's do inverse tan of infinity. Here again, we can just put all the 9s you can on your screen and then do inverse tan, and you'll get 89.999, which is a positive pi over 2. We'll bring this positive pi over 2 over here. Then you know inverse tan of 0 from here is already a 0. We're seeing a positive pi over 2 plus a positive pi over 2, and our answer over here in terms of limit evaluation is a pi, and that right there is our final answer, and we'll put a pi over here. Now let's do the same question but utilizing the graph, because you can do this by more than one means, and I'll utilize this by the graph I have right there on the side. And you'll just read the limits of that graph. Limit as t approaches minus infinity. For this part, as the function approaches 0, in all instances from the left or from the right, the function approaching 0 will always give you an output value of a 0. When you're approaching infinity here, minus infinity, your function is grazing along this horizontal asymptote, which is minus pi over 2. So here you're going to really put, as the function approaches 0, you're getting a 0. As the function approaches t, which is minus infinity, it's reaching this horizontal asymptote, it's a minus pi over 2. Simple as that. Right over here now, when you put positive infinity and you're evaluating inverse tan of positive infinity, you look at the right side towards direction of positive infinity. As you're going towards the direction of positive infinity, your curve is going up towards this horizontal asymptote, never really reaching it but trying to graze it, and your value there is a pi over 2. And then of course, as your function approaches 0 here from the right and from the left, your function will reach a y value of a 0, and that will be the graphic approach to this. evaluation, you'll have a positive pi over 2 plus positive pi over 2, and you get a pi, and that right there will be your answer. And this evaluation has been done. So in this video we talked about type 1 improper integrals which have an infinite interval, and we also talked about the involvement of the limit into this whole procedure, which is what you really have to do, because now that we are looking at limits the proper way with regards to these improper integrals, we can say that this evaluation should also bring in the word convergence, because an actual limit did exist for this specific improper integral. The fact that a limit does exist is indicated by this good value we're getting, and the fact that we could do limit determinations for this interval that we had over here, right here. We had limit determinations come into play with clear values coming into play in all instances, so we see convergence over here. And with that, I say thank you for watching this video. If you have any questions, leave them in the comments. Have a nice day. Bye.